There are some elements in periodic table which can cause detonation of a greater magnitude than a hand grenade. Sounds interesting? Alkali metals and halogens are some of the most dangerous groups in the periodic table. Why? We discuss in a moment. We are going to study group 1 alkali metals and group 17 halogens together to bring out certain similarities and peculiarities. I have divided the topic into three parts: scene 1, scene 2 and scene 3. Let me describe you about that. In scene 1, alkali metals and halogens are discussed in their elemental form or uncombined form. Elements in their elemental stage don't last long in an open environment because they are very reactive. Their high reactivity can be compared with the humans in their early childhood when they do a lot of mischiefs, very much like you people. These elements have to be sealed in containers with controlled environments. Otherwise, they will definitely react. Now imagine if you let these naughty and mischievous teenagers to do whatever they please, they will definitely cause havoc. Keep that pic of mischievous kid in your mind, and we are going to talk about a dangerous element, fluorine, which belongs to group 17 halogens. Fluorine exists as a pale yellow diatomic gas, more density than air, extremely toxic. Let me tell you, many scientists have been poisoned, blinded and killed working with the fluorine gas. Let's observe some violent reactions of fluorine. Fluorine virtually reacts with every element in the periodic table and forms very strong bonds. Fluorine is so corrosive in nature that it will eat away the whole building if there is a leakage of fluorine. It is very difficult to store fluorine in a container because it reacts with almost all substances except a few like platinum. You must be wondering whether such a dangerous element have any use. So let me tell you, F2 gas is globally used to enrich uranium, which helped in the creation of first atomic bomb. Now let's talk about an element from group 1 alkali metals, cesium. It exists as a shiny gold liquid at room temperature. Cesium is so reactive that if a small amount of it is dropped in a bathtub, it is equivalent to a small hand grenade. As soon as cesium comes into contact with the water, hydrogen gas and heat are generated so rapidly that it results in the ignition of hydrogen gas, and therefore a very high explosion is there. Now, cesium has to be stored in a vacuum sealed glass ampoules to avoid contact from the atmosphere. Otherwise, it will react with it and cause explosion. Cesium is so reactive that it catches fire in air spontaneously at room temperature. Cesium will cause burns if it comes in contact with your skin. Now, let's see some uses of cesium. I'll tell you a very famous one. Cesium is used in solar cells due to its ability to lose electrons very easily when sunlight falls onto it. We have seen how reactive cesium and fluorine are. But what about the other alkali metals and halogens? Can we predict the reactivity of other elements in the same group just by looking at the periodic table? So let me tell you, position in the periodic table has direct linkage to the chemical and physical properties. So now we are going to apply that knowledge to the alkali group's metal, which is group 1. Starting from lithium to rubidium, all are solids. of increasing softness down the group. That is, rubidium is softer than lithium. We won't discuss about francium because it is radioactive. Reactivity increases down the group. That is, sodium is more reactive than lithium. Do you know why alkali metals are so reactive? The answer lies hidden in their electronic configuration. Their general electronic configuration is NS1. Electronic configuration of all group 1 alkali metals are given as follows. If you observe carefully, you will notice that the last shell has only one electron in each of these elements. This means that as soon as this last electron is thrown out of the atom, it will achieve full octet. So, did you find out what was the reason of such high reactivity for alkali metals? Did you? You guessed it correctly. Since there is only one electron in the last shell, it is very easy for alkali metals to donate one electron and hence such high reactivity. Let's see periodic trends in halogens. Group 17. Fluorine and chlorine are gases. Bromine is a liquid. Iodine is a violet colored solid. We don't discuss about statin since it is radioactive. Reactivity decreases down the group, that is, chlorine is more reactive than bromine. Can you guess why halogens are so reactive? The answer again lies in the electronic configuration. Their general electronic configuration is Ns2Np6. The electronic configuration of all group 17 halogens is as follows. Please see it. You can pause the video if you want. Please check that the last shell needs only one electron to complete its octet. Since the halogens need only one electron to complete the octet, they get it very easily. Hence, they are extremely reactive. Till now we saw the alkali metals and halogens in an elemental form. Now we are going to study alkali metals and halogens in the combined state, that is, bases and acids respectively. Acids are formed from the combination of halogens and hydrogen, while bases are formed from the combination of alkali metals, oxygen and hydrogen element. Acids and bases of group 1 and group 2 elements are also reactive in nature, but they are less reactive than the uncombined or elemental state. Recall that we compared elements in their elemental or uncombined state to the kids or teenagers. Then we can say that acids and bases are similar to a newly married couple. Why do I say married couple? Because the new couples can be very naughty. You will find that out eventually. But they are still less naughty as compared to the teenagers. So, keeping that aside, let's take up first the acids. Acid contain loosely bound H+, which can be donated to any other compound. In acids, H+ is always attached with an electronegative atom like halogens. Acids find different uses in industrial applications. Now let's see the uses of the halogen acids. Hydrofluoric acid HF is used for etching glass, that is, to draw various patterns on glass. HF is also used in silicon chip manufacture, which are extensively used in our computers and the mobiles. HF is also used to make Teflon, which is smooth, slippery coating on the utensils You will find Teflon utensils very commonly in your houses. HF is also used in making refrigerants, used for cooling. Now let's talk about HCl. HCl is an active ingredient of toilet cleaners like Harpic. HCl is present in our stomach to digest the food. HCl is also one of the most popular acids used in the schools to study chemical reactions. HI is used to disinfect and sanitize medical tools. Now, let's see the periodic trends in the reactivity of halogen acids. Strength of the acid is measured in terms of the pKa value. Lower the pKa value, higher is the strength of the acids. You can see the order of the strength on your screen. You can pause the screen and note it down. Although HF is actually the most dangerous and feared acid, HF is not the strongest one, as you must have noticed. HI is the strongest acid in group 17. So, why is that HI is a stronger acid? HI is a strong acid because the hydrogen iodine bond is weak and breaks easily, giving out H plus ions. HF is a weak acid because hydrogen fluorine bond is extremely strong, which does not give out H plus very easily. HF is a very dangerous acid because fluorine in HF can combine with almost any substance and destroy it. HF is so deadly that even a drop of it on our skin will cause heart attack. Now let's see some bases. Bases contain loosely bound OH minus, which can be donated to any other compound. In bases, OH minus is always attached with an electropositive atom like alkali metals. Now let's see some uses of the bases. Bases find various uses such as LiOH, lithium hydroxide, is used to absorb CO2 from spaceships and submarines. NaOH, sodium hydroxide, is the most famous base used in school laboratories for chemical reactions. Also, NaOH is a key ingredient in drain cleaners of your kitchen sink. NaOH can dissolve fats, proteins and living tissues. Therefore, it is used to decompose roadkill bodies. KOH, potassium hydroxide, melts the body even faster than NaOH, but it is more expensive. On a lighter note, there is a very famous TV series by the name of Breaking Bad, in which they try to dissolve a human body in HF, that is hydrofluoric acid. So let me tell you, a human body dissolves much better in NaOH and KOH than HF. Cesium hydroxide, CSOH, can dissolve glass just like the HF, hydrofluoric acid. Now, it is interesting to note that although our powerful acids and bases can dissolve many common substances, but none of them can dissolve plastic. That is why plastics are choking the earth. Now let's see the periodic trends in the reactivity of the bases. That is, which base is stronger. So, strength of the base is measured in terms of pKb. Lower the pKb value, higher is the strength of the base. Up till now, we have seen the reactive elements and compounds of alkali metals and halogens. Now we are going to see other class of compounds which are extremely stable to our environment. that is salts. Salts are formed from the combination of alkali metals and halogens. The reactivity of these salts to the environment can be compared to the old age couple which wants to lead only a stable life. NaCl is the most famous salt. NaCl is the most famous salt. It is also known as common salt. NaCl is extremely stable. It does not react with water or air. Other salts formed from combination of various alkali metals and halogens are extremely stable, just like NaCl. Majority of these salts are actually found in seabeds deposited through millions of years in the sea. These salts are the biggest source of alkali metals and halogens. Throughout our lecture, we saw various phases in the life of alkali metals and acids, that is, in elemental stage and in compound stage. And finally, what we have arrived is salts. Salts are also compounds but are not reactive, not as reactive. Thank you.